it's actually like you start with a unital sister algebra and you have a faithful state, and you say that an orthogonal filtration is actually a sequence of finite dimensional subspaces with the notation that A0 is the complex number, and when you take the span of the union, this is dense, and orthogonality means that if you have this condition is 0, then they belong to two different components. So this means that the orthogonal with respect to this state. And then we call this triple, which we usually write like instead of writing this triple explicitly, we simply denote it by the script A. Okay, and the most important example is if we have a discrete group and if we have a length function, then we define this subspaces as span of this regular representation where the length of G is n, and this forms a filtration with respect to the canonical trace on the reduced group sister algebra, and we denote this as B. So if so far, I mean throughout in our talk, whenever we will encounter a like any sister algebra which has and some discrete group, then the corresponding filtration will be denoted as script B, and script A is fixed for some, I mean for a fixed filtration on a given day. Okay, now given an orthogonal filtration, as it is, I mean, like Banik and Skalski, they actually managed to construct a notion, I mean, a quantum symmetry group as an universal object in a certain category. And of course, these groups are, I mean, these quantum groups are compact quantum groups. So before we do, so this is just a repetition of what we have seen in the morning. It's a standard definition of a compact quantum group. It's like it's by Voronovich, and it starts with a unital sister algebra and a unital star homomorphism, which satisfy these two properties. And roughly speaking, this definition was motivated from the concept that if you have a compact semi-group with cancellation, then it's a compact group, and this definition is the non-commutative analog of that. Now, for a compact quantum group, given any quantum group in general, locally compact, doesn't matter. So if given any quantum group, there is actually a dual object. So if we have a compact quantum group, the dual is a discrete quantum group. And not only that, this duality is given by some unique unitary operator or unitary of the multiplier algebra, and this actually encodes the dual pairing between G and G hat. And this is called reduced by character for a compact quantum group. And standard example, if we have a compact group, then the algebra of functions forms a compact quantum group. If we have a discrete group, then the reduced group sister algebra or full sister algebra, both of them with respect to this group-like co-multiplication map, forms a compact quantum group. One thing to notice is that if we have a discrete group, one can associate two compact quantum groups for a given discrete group. This version is the reduced version, this is the full version, and one can do the same, one can play the same game for any compact quantum group. And in general, these full and reduced versions are not isomorphic, but if the group happens to be amenable, then they are isomorphic. So in this case at least.
What is the difference? What is the difference between delta and
no, so the idea is for both, like reduced or full, the same delta works.
Okay.
So it's just you take an element and you just map it to X tensor X.
So what is the difference between them?
The difference is in the algebra. They're not the same. This is much bigger.
In what way?
So this is set of all, like this is, so okay, you just take the L1 of G and then represent it into L2, and now consider all possible representations and take the closure. That gives you the C star. And if you just do it with respect to the regular one, that gives you the reduced. And they're not isomorphic. And
So
they are isomorphic.
groups.
Sorry?
Gamma is infinite.
Of course, yeah. If it is finite, then of course they are isomorphic, correct. Okay. Now action, the notion of an action of a compact quantum group, this was also mentioned in Goswami's talk. And it's actually, so we call either action of G or the coaction of C of G. So this is just a standard terminology. So it just satisfies this some compatibility condition, and it satisfies some extra condition called the portlet condition. And this notation, by the way, means, or in the previous slide also, so if we have something like this, this means basically you are just taking the closed linear span. So just it's not just the product, it's actually the linear span and take the non-closure, and if you get this. And similarly, one can talk about the coaction of the universal one, like as I mentioned, that for a group, discrete group, infinite discrete group, you have two versions of compact quantum groups. Similarly, for any quantum group, you can talk about reduced version and full version. So one can similarly define the universal version as well. And it's a very nice result to know, and it's actually quite handy for us. It was proven by Fisher back in 2003 that if you have an injective coaction of a reduced quantum group, you can always lift it to a coaction of the universal one. And of course, if you have a universal one, you can always construct a reduced one. But the question is whether you can lift it. And it turns out that if the coaction is injective, then you can always lift it, which is actually a very important result. And these coactions are sometimes called normal coactions. And CQG morphism means you have a Hofstad morphism, meaning you have a algebra homomorphism, which is compatible with respect to the co-multiplication maps, which intertwines the co-multiplication map. And secondly is, let's say you have a C-star algebra and you are having action of two compact quantum groups on it. And if you have a quantum group homomorphism from C of G1 to C of G to C of H, then you say that this CQG morphism intertwines these actions if you have this condition. So it's basically like you have in a way that you are considering this category of algebras with a group action. I mean, in a way. Now, quantum symmetry group is a universal object of some category, and this category is the following. So you fix an orthogonal filtration, and then you consider the category where the objects are pairs, where the first component is a compact quantum group, second component is an action of G on this C-star algebra, which preserves the filtration. Meaning, if you act on AI, it actually stays in AI tensor C of G. And morphisms are just CQG morphisms which intertwine the actions, action in the previous sense. Now, once you are in this situation, then Banita and Skalski proved that in this category there is an universal initial object, and this object is in the category, therefore it's a compact quantum group, and it acts on the given C-star algebra faithfully. Faithfully means it's not that a subgroup of it is acting, it's actually the whole group is acting. And one remark here, this is important to know, it is important to mention that this filtration preserving action which preserves the filtration also preserves the state. And preserving the state means these actions are always injective. But the converse is not true, meaning if it preserves the state, it doesn't imply that it will preserve the filtration. So this is an important observation. It is, just at this point I'm making so that this will be crucial in a later stage. Now, the starting point is if we have a C-star algebra with an orthogonal filtration, we know there is a quantum symmetry group. Next step is, let's say we have a C-star algebra and we have a discrete group acting on that C-star algebra. Discrete group with a length function. That means the reduced group C-star algebra also has an orthogonal filtration. Question is, of course, if we have an action of a discrete group on a C-star algebra, then one can form a cross product by this way. Question is, what about the quantum symmetry group of this? Can we say anything? If we can, is it possible to relate the quantum symmetry group of this cross product in terms of the quantum symmetry group of A and the quantum symmetry of the reduced group C-star algebra? This was the starting point of this whole project. Okay. Now, just these are the standard notations. So, just shorthand of this beta A times 1 tensor lambda G. This is the regular representation. So we write this as AG, and then we actually, using the canonical conditional expectation, we actually define a a state on our cross product, which is basically the linear extension of this. And finally, we define subspaces where AI, gamma, lambda, gamma, j, where the AI is in the filtration AI, capital AI, and the gamma j is the length of this is j. So we define, actually we are trying to define an orthogonal filtration for the cross product. That's what we are trying to do. Now, what this was actually, originally this result belongs to, well, this is in our article, but this was, this was actually originally goes back to Mondol and Skalski. What they actually observed, that if the action preserves the state, then this with respect to this tau forms an orthogonal filtration for the cross product. So here the most important assumption is the action preserves the state. So if the action is the state preserving, so then one can construct the orthogonal filtration of the C-star algebra. So under this condition, one can show that the quantumized symmetry group of the cross product exists. Not only that, they computed one example explicitly in one particular example. What they did is, they just took C-star algebra of Z9, and then they just took gamma to be Z3, and then they just let it act on Z9 by automorphisms. And this induces this, like in the coaction notation, this induces a coaction. And they actually, this is the most crucial part, they actually computed the Q iso of the cross product. And it turns out this is actually direct sum of C star Z3 cross Z9 cross Z3 and the same. Now it has a vector space dimension is for 54 because simple calculation 27, 27 and they add it up. Okay, but next thing which we wanted to understand, because let's say you have so this is actually a standard way of thinking, or the canonical way probably, is if you have two algebras and if you, let's say, know some property for the both algebras and you form the tensor product and you ask whether this property, how this property is reflected in the tensor product from the original perspective. So that's what we wanted to understand. Now we wanted to understand whether the Q iso of this object is somehow related to the Q iso of the factors. Now it turns out, on the other hand, the Q iso of Z9, Zn in general, for n not strictly not equal to 4 is the direct sum. Therefore, the vector space dimension of C star Z9 and C star Z3 is 108. Which means, if you just, because the cross product, reduced cross product, contains both of these algebras, as a vector space they are actually isomorphic. But what happens is, if you just consider the quantum isometry group for these two components, one hand, for the cross product we are getting 54 dimension, and the other hand we are getting 108. So there is a huge dimension drop. And though, so the idea is, though we can compute under certain assumption, we can say, okay, the quantum symmetry group exists for the cross product, but we are not able to relate, or we are not able to say anything in terms of its factors. That's exactly the mysterious part, and where actually this whole game started. So what we decided to do is, instead of doing it only for the reduced cross product, let us generalize the whole setup. Let us try to do it in much more general situation. And here it comes, the twisted tensor products. So before we go to the twisted tensor product, so the idea is, it's like generalize, you have tensor products and you just twist the multiplication map of the tensor product. That's the idea. So you have two C-star algebras and you have two orthogonal filtration. So here this B is not necessarily reduced group C-star algebra. It's actually a general limit C-star algebra. And then you have this standard canonical actions, gamma A, gamma B, the canonical action of the Q isos. And this is the most crucial assumption. We assume there is a bicharacter in the dual. What it means the following: a bicharacter between chi living here is equivalent to have a quantum group homomorphism from QIC of QISO of A to C0 of the QISO of B dual, or the dual of this. So basically, just notice that this is like if you have two abelian groups, and if you have a group homomorphism from G to H, then it induces a group homomorphism from H hat to G hat. This is exactly the thing, and this is something which follows from the general result that we have on homomorphisms of quantum groups. Now, so that means we are actually assuming some interaction between the Q iso of A and Q iso of B. So that is something we are assuming. Assuming this, we can form a twisted tensor product of A and B. So this construction, one can do it in more general, like for any two sister algebras with some quantum group coaction and some bicharacter. And this was somehow we investigated this because we wanted to, in a different context, we wanted to understand the Radford's bosonization in the operator algebraic setting. But anyway, but in this context, we just use not the full machinery. We just use the restrictive one. So what we do is, so if we have a bicharacter, it already gives rise to a pair of representations on a Hilbert space, which we call Chi-Heisenberg pair. Roughly, it means that it tells you that this so these actually W's you can view, they are actually regular representations of Q iso A and Q iso B. And roughly this Chi-Heisenberg pair representation just tells you how the regular representation commutes. And actually it commutes up to the factor chi. That's what it says. Having this pi 1, pi 2, you can define a map from A to multiplier algebra of A tensor B tensor K of H. Simply just first apply gamma A, which will you'll be there. And then on this component you apply pi 1 and then embed it in 1 free. And similarly you just apply gamma B, embed it, and then you just apply, sorry, it should be pi 2, apply pi 2 and then embed it here. And it turns out that if you take the closed linear span of J1A, J2B, this becomes a sister algebra. And since A and B both are unital, this will be a unital sister algebra. And this unital sister algebra we call the twisted tensor product. Now what we wanted to understand is whether we can talk about quantum symmetry group of this object. Why? Because reduced cross product is a special case of this construction, where you choose your B to be just the reduced group sister algebra. Okay. Not only that, there are some other class of examples as well. So next question is whether we can form an orthogonal filtration on this twisted tensor product. Answer is yes. So first of all, given this function of states tau A, tau B, one can straight away construct a functional, just a functional on A box B. Next step, what we proved is this is actually a faithful state, and this one J1 AI, JA AI, JB BJ, this forms an orthogonal filtration with respect to this state. So what we proved is on A cross B, if A and B, on A and on B, if you have an orthogonal filtration, you can construct a canonical orthogonal filtration on A box B, which means existence of quantum symmetry group is guaranteed. Now the question is, can we identify that quantum symmetry group in terms of some known object? And this is surprising. Drinfield's double comes in the picture. What we do is, this is actually in the algebraic framework, this was known long back. And in the compact quantum group setting, nobody, I think, looked at it explicitly because nobody needed it. But yeah, okay. So it's basically Drinfield's double of this Q iso A and Q iso B is again a compact quantum group which contains both of them. It's actually roughly just the generalization of the direct product of quantum groups. And this, direct product with a twist, and this twist is given by this bicharacter chi, in a way. And just observe that the co-multiplication map is nothing but just like just the co-multiplication map of the factors, and you just embed them. So in a way, the algebra is, because see, so it is not guaranteed that this rho and theta will commute. In general, they don't. So algebra is twisted in a way, but the co-multiplication is not twisted. That is what, that's how it is viewed. And this pair of representations, rho and theta, they are called canonical Drinfeld pair. And what do I mean by that? It basically satisfies this hexagon equation, this Young-Baxter type equation. And there is actually a universal Drinfeld pair, which means that because for every reduced quantum group there is a universal version, one can lift. This is something we proved, that lifting was not difficult. Proving that that this existence of this rho u theta u, the difficult part was to prove that it is also a Drinfeld pair, meaning it also satisfies some equation like this. That was actually a hard part in this context. And though we needed it only for compact quantum groups in our context, but we did it in complete generality for locally compact quantum groups. Okay. Now, again, this is not a new result in the algebraic setting, but in the sister algebraic setting, again, nobody looked at it. And this is something I did long back for locally compact quantum groups, but here we are using only for the unital case. So basically, there is a canonical action of the Drinfeld's double on the twisted tensor products. It's like if you have a group G acting on A and H acting on B, then G times H acts on A tensor B. But here, this tensor product is twisted by chi, therefore this direct product is also twisted by chi. And that twisting is the Drinfeld's double here. And the action is again just like the standard action, like it behaves like the action of factors if you restrict the action on A and on B component. Okay, now notice that by the Fisher's theorem or the Fisher's result, if we have an injective coaction of the reduced version, there is an coaction of the universal object. So there is an universal coaction. This follows from the result of Fisher. But what we proved is this universal coaction is also, like if you restrict on the factors, it will behave like that coactions on the factors, individual factors. So in other words, now from this formula, these two formula, it is not hard to check that these coactions actually preserve the orthogonal filtration of the A cross B. This is just like if you just go through the formulas, it is not very hard to check using this formulae. In other words, what I'm trying to say is the universal, so this Drinfeld's double becomes an object in the category of A cross B, which means there is a quotient map and it acts faithfully. This is also something we proved. Therefore, there is a quotient map from the QIs of A box B to the D chi, the Drinfeld's double. For the other direction, we actually proved some universal property for the universal Drinfeld's double, and we proved that there is actually a map which takes it back, and the composition is identity. And then we concluded that the QIs of A box B is isomorphic to the universal Drinfeld's double. So in other words, in this setup, if you know the QIs of A and QIs of B, you can actually talk about the QIs of A box B, and that is nothing but something which is very, very known object, Drinfeld's double, generalized Drinfeld's double. Okay. Now, the standard corollary is if you just take the bicharacter to be identity, then this twisted tensor product is just the standard tensor product, and the Drinfeld's double is nothing but the tensor product or direct product of quantum groups. How do you view it? It depends on you. Okay. But what about the examples? It turns out that Riefel deformation, because first of all, maybe it is better to read the last line first, that if we have A and B two unital sister algebra and you have an action of GH compact abelian groups acting on them, and if I assume there is a bicharacter, then the Riefel deformation of A tensor B with respect to this, with respect to a cocycle induced by this bicharacter is nothing but A cross B with respect to this this cocycle, this bicharacter psi. Now, if A and B, this action preserves the filtrations, then one can actually, one can show that the Q iso of E psi, the Riefel deformation, is nothing but the Q iso of this, and we have identified this with the Drinfeld's double. So this follows. Fine. Now let us. So we actually somehow generalized our setup and we answered some question, but it doesn't still answer the reduced cross product situation. So let us revisit the situation. So this is again the previously written things. I just wrote it down for the sake of completeness. It's just a repetition of the same slide. The setup. Now, we had to make an hypothesis because what we want to do is we want to, so technically, I mean not technically speaking, honestly speaking, we couldn't answer the general reduced cross product situation. But under certain hypothesis, we managed to answer that. What we did is we put some hypothesis and such that the reduced cross product situation will be a special case of the A box B. It will lead to that, and then we will be able to identify. So what we did is we just said that, okay, assume that there is a quantum group homomorphism from Q iso of A to CB of gamma. It means you have a quantum group homomorphism like this. This is just an hypothesis. This hypothesis actually gives you, it's actually quite magical. What it does is, first of all, using this quantum group homomorphism, and this gamma A of U is the canonical action of Q iso of A Cu on A. This induces an universal coaction of, okay, this should be C gamma. Okay, no, this is fine. So this gives you a coaction of gamma on A, or action of gamma on A. This formula induces. Not only that, this Aij becomes an orthogonal filtration. Remember one thing, this thing that if action preserves the filtration, then it preserves the state, but the converse was not true. So this is crucial here. Here, I am not assuming that the action preserves the filtration. I am just assuming, because see, gamma preserves the state. Therefore, this beta will also preserve the state. Okay, but I am not assuming that it will preserve the filtration. So the other way. It preserves the filtration, therefore this will also preserve the filtration. That is the crucial part here. Now, this data gives a canonical bicharacter. This is, if it looks scary, it is not at all scary. This is actually a standard manipulation. You have to simply start with the bicharacter for C0 of gamma, and then you have to just manipulate, and then it canonically gives you this bicharacter. Actually, to be very honest, this hypothesis we derived by a back calculation from here, to be very honest. And finally, once we are in this situation, we actually can conclude that the Q iso of the cross product is isomorphic to the Greenfeld's double for the factors. This is just goes. I mean, once you have these, then you can actually simply manipulate this. This becomes a case of the general twisted tensor product situation. Question is how practical this hypothesis is. Fine. Under this hypothesis we can identify. Very good. But whether there are examples or there is any example which falls or satisfy this hypothesis, the answer is actually the class is not that small. It is quite large indeed. Actually, on the contrary. So what we did is, it's just standard group homomorphism, the duality between Zn and Tn. Using this, we have a quantum group homomorphism. Now suppose that there is a quantum group homomorphism from Q iso of A to C of Tn. In other words, this means that Tn is a closed quantum subgroup of Q iso of A, in a way. So it is a sufficient condition, of course, which means that if there is a maximal torus inside the quantum isometry group, we are in this situation. And having this, now using this G hat, you can define an action of Cb of Zn. So this means you have a quantum group homomorphism from Cu of Q iso of A to Cb Zn, which means you are satisfying the hypothesis, and you define the beta. And with respect to this beta coaction, construct the cross product, and then once you construct the cross product, you can say, okay, the quantum isometry is isomorphic to the Greenfeld's double of the factors. Class of examples. First one is, take a compact Riemannian manifold where this is tau is the integration with respect to the volume, and then orthogonal filtration comes from the eigenspaces. Now the quantum isometry or the isometric group of C of M will have a maximal torus, because it will have a maximal torus. Therefore, we satisfy the hypothesis. Meaning, this will be in this situation, and therefore this will lead to this situation, and therefore we are satisfying the hypothesis. In particular, if we take M to be T of Tn, the resulting cross product algebra will be the non-commutative 2n torus, and then the Q iso is will be the Greenfeld's double with respect to that, which is actually previously known result. Similarly, if we have a Q deformation of compact semi-simple Lie group where tau is the hard state, then the orthogonal filtration comes from the matrix coefficient of the irreducible representations. This will be also in the same class. Moreover, if we have quantum homogeneous space by a closed quantum subgroup, we will be in the situation when we have Kunz algebra, the orthogonal filtration constructed by Vanicka-Skalski. Twisted cross products. Like if we have a cross product and we twist the cross product by a cocycle, this will also fall in the same category provided beta satisfy the condition, because in particular if we choose your cocycle to be trivial, it should at least fall in the same category. So if beta satisfy the condition, then this will also fall in the same class. Finally, this Boons-Dedens algebra, sister algebra, this also falls. So we have actually a large class of examples which is covered by our construction. I mean, though it is a very restrictive, under very restrictive condition it works, but still that restriction is not that bad. At least this list shows that. Counter example. Now question is, we proved under this hypothesis we can prove that the Q-iso is isomorphic to the Drinfels double. Question is, what about the converse? Unfortunately, we don't know, but we have sufficient evidence to justify probably this is necessary and sufficient, but we don't know. So let's just revisit the example which we discussed in the beginning, that the Q-iso has dimension 54, whereas the tensor product dimension is 108. So it turns out in this example the hypothesis is not met. So this beta, the action, does not come from some quantum group coaction as mentioned in the hypothesis. So in this context the hypothesis is not met and we have this dimension drop. So it seems, or it actually, this somehow forces or suggests that probably this hypothesis what we put is probably necessary, but we don't know because we just like have only one evidence of one counter example, and we don't know whether this will fall in this like whether this is necessary and sufficient. It will be good to know if it becomes necessary, but to be very honest, as I started, like it was not our intention to prove a necessary sufficient condition. By the way, we wanted to prove, or we wanted to understand the Q-iso for the cross products. So that was our goal, and under very strong hypothesis we managed to prove this, and I think that's more or less all. Thank you.